Hello everyone, my name is Joe Scorsone, channel called Ethernet. In today's video, we're going to be doing episode 19 of the Quant Finance Advent of Code. Today's video is about isolation force and outlier detection in time series. So yeah, we're going to hit it, we're going to get into it. Before we do that, I want to show you guys my X account. Thank you guys for all the growth on this. I'm the most active on this. You guys can interact with me, get updates as soon as possible on here. Algo caught that low. Algo caught that whole thing with FOMC. Of course, you really don't know what happened with FOMC, but you could have just listened to the algo, stopped out with the algo, and you could have been fine. Yeah, this is the algo though, through Lux Algo. There's more details about this in the description. You guys can check this out. You can apply it to your trading view charts if you'd like to actively trade. But yeah, today we're going to be implementing isolation forests. So I have it, like this is from scikit-learn, the actual package. So we're just going to be doing this, like seeing what's actually going on under the hood. Of course, it'll have a bit less parameters than the scikit-learn one, but we just needed to do what we needed to do, which is implement an isolation force from scratch to find outliers in stock data, plot with Plotly. Simple enough. So we still have just the cache in our get data. So now let's get into our main, and then we're gonna see where we go from there, and then we're gonna get into what the isolation force actually is doing. So, and just so that way you guys can see, just not importing it. So yeah, that'll be good. So we're just going to do it on queues, start and end dates, get our stock data. Good stuff. So now for every ticker and data frame in there, we're going to copy it so that way Pandas is happy. We're going to get the log returns, drop our NA, and then we need our X variable to be our log returns, but reshaped. It has to be a 2D array with one column. So instead of an array just going to the side, we just need a column. So there we go. Then we're going to initialize an isolation forest with 100 trees and a max depth of 10. We're going to fit it to our X, and then we're going to predict if each data point is an outlier or not from X. So then we're going to get it into an outliers column, get our index for it, and then we can plot it. So yeah, that's pretty much all that's going on in main. The actual isolation forest class that we have is as follows. So just simple initialize self dot number of trees is number of trees, max depth is max depth, and the amount of trees that we have because it's a forest, right? The amount of trees is a list. So to fit it, we're just going to make sure that this self dot trees always gets empty as we refit it. So now for every tree that we have, what we're going to do is randomly sample half the data for each tree. So we're just going to do it like this, a random choice with the floor division of 2. Make sure that we have the shapes right. And then we can get the sample indices. We can get the sample is going to be that sample from X. Then our tree is going to be an isolation tree, right? This is the forest. We need trees of max depth. Fit the tree with the sample and then append that tree. So now let's take a look at these. Actually, let's finish this class before we go into what the individual trees are. So now this anomaly score, it needs the X. And so we need to find the average path length across every tree in the sample. So pretty much how far is every tree from another one on average. Normalization constant, this is just a constant based on the size of X. So just something that we need, so that way we can return 2 to the power of the negative average path over this constant. Then the score will be an anomaly score from that, and if the score is over a threshold that we set, default I have it set at 0.7, then if that is true, then that is an anomaly, is what we're saying here. So yeah, and this is based off of how far each tree is from each other. So that's why, isolation tree is contextual. So now let's look at this tree. So it is a tree, right? But it has some more detail with it. If you guys are in college and you've already taken your data structures and algorithms, it'll be a good refresher. Yeah, and there is just context with it to be an isolation forest. So regardless, max depth is max depth. Initialize all these things to be none. Split features, split value, left, right, and size is all none at first. So now, so now let's just do path length first because I want to spend a smidgen more time on this. So path length, actually, no, because we have leaves. That's okay. So we have n samples and n features is x.shape. So now, if the depth is greater than the max depth, or the samples is less than or equal to 1, then we're done. We either reached our depth, or there's only one sample left. Either way, we got nothing to go off of, so the size is n samples. So now choose a feature randomly for splitting. So, and I should set, I always forget to do this. I should set a seed just for replicability. So set our seed to be 2024, split feature at a random feature. Feature values is X's split feature. And then the min and max values is that feature's min or max. And the feature values will be X up to that feature. So now, if every value in the feature are the same, then it's a leaf, meaning that there's nothing coming off of it. It doesn't have a path to another tree. It's just a leaf. It's just there. Or it doesn't have a path to another node. It doesn't have a path to another thing. Let's bust out the paint here. Let's bust out the Microsoft Paint. So if we just have a tree, right? I'll do it like this, right? Like these two are leaves because there's nothing else around them. You know what I mean? But these are considered leaves because they still keep going. That's all that is. If the min and max values are the same, then it's a leaf. Now we're going to randomly choose another value from the range of the features. From the min and max value, we're going to pick a random value in that range, within that range of the min and max. The left max, so the left side of the tree, pretty much the left mask is the feature values less than the split value. So this random value, if the feature is less than it, then that is the left side, and the right mask is the opposite of that. So the tilde is the bitwise nod, so every 0 is a 1, every 1 becomes a 0. And then we're going to recursively build the tree from the left and right subtrees. So the left tree is an isolation tree of max depth, the right tree is an isolation tree of max depth, and so then it's pretty much the same, but just with the different sizes. So we're going to fit the tree to be X is left mask, and it's going to be of depth plus 1 because, extra nodes. And then the right is going to be the exact same thing, but just the opposite of the left. So there you go. Then if the path length, well, to find the path length, we need X, we need our our data. If the self.size, like the actual size we have here, is not none, then we can just return this. If it's not, then we need to actually get the value. So if the node is a leaf, return the path length based on its node size. So this is the length of the path. So now, if that's not the case, we need to get the value of the split feature for every sample. So again, feature value, does that look familiar, right? What am I trying to say? Feature values is the X up to the split feature, and then left mask is the feature value less than the split feature. Right mask is the absolute opposite. Absolute opposite is a weird way to say that, but it's just the opposite. It's the bitwise not. Path, we're just going to initialize it to be zeros. So then if we're on the left, the path left mask is the path length for the left mask, and if it's right, or if we have data to go off of, right? So if these two exist yet, then we're just going to find the lengths of each path and then just add 1 to the path for the current node. So all those paths, pretty much saying on or off, is how we're going to find the outliers. We're going to find these average path lengths for each side. Or for each tree, we're going to find each tree's path lengths. Put it over our constant like that, and then we can find the anomaly score through that. That is what this is. And then, yeah, our scores, if the score is over the threshold, that means that it's an outlier. Pretty much meaning through for every data point that we have, on average, each data point is X distance from the other one. Doing it in this method with trees and with distance from each tree. If one is further away than all the other data points, for whatever reason, that point is an outlier. So now let's visualize this. Oh. So there we go. Here we are. So that is what I didn't put dark mode on. I'll do that right now, but yeah. So here is where every outlier would be, and we could see that it's obviously it's a pretty black box. We don't actually know what's going on. We know the steps that we're giving it, but we could see how this one would be a decent trend follower, with this one just marked at top perfectly. So pretty much in a way, the way that I would use this was like, I have an outlier right here, so I should look for rare trades here, in the sense of like a mispriced option or something like that, or just something moving out of line. Maybe something is just cheap, something's expensive. There's something going on over here that I could take advantage of, right? Either we're underpricing or overpricing something. So now let me hop in here, update layouts, and I want to probably dark. I believe that's all I have to do, because I just think it looks so much better in dark mode. Yeah, there it is. That's so much easier on the eyes. But yeah, that is the video. That is how to spot out there. How to spot outliers in price data using an isolation force. I think it's a really, really cool method. I think it's a straightforward method. I think it's a complicated, straightforward thing, and that's the kind of stuff that I love. Take a sip of coffee. I love complicated, straightforward things. What I mean by complicated, straightforward things is like in my mind, a Garch model is straightforward, but it's complicated. It really is complicated. A neural network is straightforward, but it's complicated. We're going to code a neural network from scratch at some point in the series. I have one in Scratch from C++ in my GitHub if you guys want to check that out. But yeah, I just love stuff like that. I love stuff where it's like, this is my task. This is my goal. I need to find outliers. So I'm going to make a fucking isolation force. You know what I mean? That's the kind of thing that gets me giddy. That's the kind of thing that I enjoy. So yeah, I encourage you guys to check out this code on my GitHub. I encourage you guys to break it. I encourage you guys to make it better. I encourage you guys to try it out on different equities, or whatever vehicles you want to try it on. I encourage you guys to play around with this threshold, because if I were to just drop it to 5, then we could see the difference. So see, now pretty much everything is a damn outlier. Almost every single day in a row, which is pretty damn interesting. And then if we were to set it to like 9, potentially none of them would be, right? So there's also definitely a way of overfitting this, which is always something to worry about, right? So finding sweet spots, finding values that explain as much as you would want explained, and not more, not leaving too much out. That's the name of the game. Everything's pretty much as good as those values can be. So yeah, that's the video. This code is all on the GitHub. We're almost all set with this. Pretty fun to make. I'm going to take a hiatus from YouTube when I'm all done with this. But yeah, hope that you guys enjoyed this video. I will catch you guys in the next one. Goodbye.